In the last video we defined topological spaces, and remember a topological space was a set equipped with a collection of subsets that we think of as open sets. And in this video I'm going to tell you, given a set, how might you specify a topology? How might you pick out the set of open sets? And the idea comes from metric spaces. So I'm going to first tell you, given a metric space, X with a metric D, how do I define a topology on X? Well, what I do is I first form the set curly B, which is the set of all balls of some radius around some point. X ranges over all the points in X, and R is just any number. So let curly B be this. So this is the set of all balls. Then what I do to form a topology is I let T be the set of unions of open balls, just arbitrary unions. Of balls in B. And the claim is this is a topology on X. It's called the metric topology. And in general, this is a very good way of defining a metric, a topological space. You specify a collection of sets, and then you take arbitrary unions of those sets. So when you have this kind of situation, the set B is called a base for the topology. In other words, T is obtained by taking unions of sets in the base. Okay, so let's prove the claim. Is the empty set in T? Well, T is a set of arbitrary unions of balls in B. In particular, you're allowed to take the empty union, where you're just unioning nothing, and that gives you the empty set. So that's certainly in T. What about X? Is X in T? Well, yes it is, because I can take any point in X, look at some radius around that point and take the ball, and then if I just take the union of all those balls, I'll get every point. So that says X is in the topology. Unions of sets in T are unions of balls in B, so in particular they're unions of balls in B. So they're in T, just by definition. So all we really need to check is that the intersection of two open sets in T is again an open set in T. So we need to show that if U and V are in T, then U intersect V is in T. So for this, I need to prove that if I have U and V and I have a point X in the intersection, then that point is contained in a ball which is contained in U intersect V. And what I know is, because U and V are both in the topology, I know that X is contained in some ball of some radius around a point little u that's contained inside big U, and I know that X is contained in another ball of some radius t around a point little v, and that that ball is contained inside big V. Right, so the existence of the red ball and the blue ball follow from the fact that U and V are in T. What I want to show is that there's this green ball which is contained in the intersection. Because then, if I just take the union of all the green balls, that will exhibit U intersect V as a union of balls, which is how I defined the topology T. So all I need to do is to pick some radius for this green ball that's sufficiently small that it's contained in both the red ball and the blue ball. So what's that radius going to be? Well, let's see. Here's our U, here's V, sorry, X, and I need to pick a radius such that the ball around X is contained inside this red ball. The red ball has radius S, and this distance here from U to X is something. And what's left? This radius here I'll call epsilon 1. That's S minus the distance from U to X. So if I take that radius epsilon 1, I claim the ball around X of that radius will be contained inside the red ball. So let's check why that's true. Suppose we have another point W. So if W is in the ball of radius epsilon 1 around X, then I claim W is also in this red ball, and that's because the distance between W and U is bounded above by, well, by the triangle inequality, it's bounded above by the distance from W to X plus the distance from X to U. This is less than or equal to epsilon 1. It's strictly less than epsilon 1 actually. And epsilon 1 is S minus dux, but we've got a plus dux here, so overall this is less than S, which is what I want. That tells me that W is in the ball of radius S around U. Okay, so if I pick a radius that's smaller than epsilon 1, then this green ball is going to be contained inside the red ball. Similarly, I can define epsilon 2 to be T minus the distance between V and X. And whichever of these is smaller, I'm going to take that one and call it epsilon. And now the ball of radius epsilon around X is contained in the intersection of the red ball and the blue ball, and in particular that's contained in U intersect V. Okay, so that completes the proof. So we can take away a moral from this proof that we've just seen, which I'm going to write as a lemma. which is let X be a set and let B be a collection of subsets, let T be the set of arbitrary unions of sets in B, then T is a topology if some conditions hold. Let's go back and examine the proof and see what we actually need to check. Did we need to check the empty set was in T? No, it followed it automatically by taking the empty union, so that doesn't need to be added as an assumption. Did we need to check that unions of sets are in T? No, because T was defined as the set of unions of sets, so we didn't need to check that either. We did need to check that X is an open set, and what did we do? We said, well, every point X is contained in some ball, therefore X is a union of balls. So we need to add this as a condition. For all X in X, there exists a B, little b, in B, such that X is in little b. So this is the thing that will imply X is in T, and we needed to check that intersections were in T. And what we actually did, if you examine the proof that we just did, we showed that for all balls U and V in curly B, and for all points in the intersection, there exists a little b in B, which is the green ball in the picture, such that X is in little b and B is contained in U intersect V. Right, that was this picture here. That then shows the intersection of U and V is made up of balls from B. It's a union of balls from B. And then if you take unions of U's and V's, then the same argument applies. Okay, so this is the lemma. And if these conditions hold, we say that B is a base for the topology T. So I want to use this now to define what's called the product topology. So this is a way of generating new topological spaces. So if X and Y are topological spaces, we can put a topology on their product, X times Y, by specifying a basis. Or a base B. In this case, the base is going to be the set of sets of the form U times V, where U is open in X and V is open in Y. This is maybe what you would expect open sets to look like, but you're also allowed to take unions of such things. Let's just draw an example, right? So the square is the interval times the interval. And things like this subsquare, open subsquare, is something of the form u times v, where this is u, this is v. And I could take another square, I'll do it in red, maybe this one, which is also of the form u times v for some u's and v's. But the union is also an open set, but it's definitely not a square. It's not, or a rectangle even. It's not sort of u times v for anything. It's just some weird shape. So that's not in the base, but it is in the topology. So we need to check that B is a base, i.e., let's just go back to our requirements of a base. We need to check that every point is in one of these basic open sets, and that intersections can be written as unions of basic open sets. For all now xy in x times y, we want to show that there is an open set of the form u times v that contains that. Well, certainly there exists a u open in x such that x is in u, and a v in y such that little y is in v. So x comma y is in u times v. Right, so that proves that every point in the product is contained in one of these basic open sets, because you sort of project down to one factor, find an open set containing it, project the other factor, find an open set containing it, and take the product of those two. And we need to check that if we have u1 times v1 and u2 times v2, these basic open sets, then their intersection is a union of basic open sets. But actually you can kind of see from this picture, maybe I'll make it a bit bigger. If I just have a rectangle and I intersect them, I get another rectangle. Right, so the union is not a rectangle, but the intersection is a rectangle. And that's true because what's happening here is u1 times v1 intersect u2 times v2 is the same as u1 intersect u2 times v1 intersect v2. And if u and v are open, u1, u2, etc., all open, then u1 intersect u2 is open and v1 intersect v2 is open. So this is a basic set. In particular, this is a union of basic sets. So that implies the intersection is in the topology. So that tells us that B is a base. And the topology it defines is called the product topology. Sorry, the topology it defines is called the product topology. So specifying a topology by writing a base for the topology can be a very efficient way of working. In the next video we'll see a different way of doing it for constructing topologies on subspaces. So that's next.